See, it's more complicated. Anyway, so supersymmetry, we don't know, maybe supersymmetry is realized, maybe at very high energies, maybe at Planck scale, maybe at string scale. And I will comment on this, and you may ask me more later. So, eventually I will meet each of you in my office, and I will ask what are your interests, what are you doing, what is your knowledge. But just to start, how many of you had courses on standard model in your university? 1, 2, 3. Okay.
But I mean, supersymmetric standard model, yes, but normal no.
Well, you jump already, you know, to higher level, right? That's very dangerous, by the way.
It's on the projector.
Oh, so projector is shut off. By the way, I will use projector also. And how many of you had courses on particle physics and nuclear physics, particle and nuclear physics? I see. Okay. So, how many of you want to do particle physics in future? And the rest are biologists, no? How many cosmology and astrophysics? How many of you want to do cosmology?
String cosmology, yes.
String cosmology. Again, too complicated immediately. Immediately. So, and string theory? Okay. Good. So, let me say a few words about my course. And so we will study particle physics. And more precisely, experimental and phenomenological basis of the standard model. And standard model is considered these days as the theory of elementary particles. So this is what is kind of the deepest understanding of nature, the standard model. Of course, there are many speculations beyond the standard model, but nothing is confirmed yet. So this standard model is really the theory of particle physics. So what I will discuss mostly experimental and phenomenological basis of the standard model without discussion of the standard model. And then in the second part, and that will be next semester, it will be really presentation of the standard model. So I will discuss the main notions and principles and ideas behind the standard model, without again touching the structure of the standard model. And as you will see, that many things can be already discussed and understood even without explicitly using the standard model. So what I will show is how main elements of the standard model emerge from the experimental data, from our observation, and how this idea is developed. I believe this is the most efficient way really to understand what happens when you know the history, why we introduced this notion or not that one, and how this development occurs. I think that should be really a right way to present things. Now, what is the standard model? Standard model is Lagrangian of certain type. And using this Lagrangian and quantum field theory, you can describe all the phenomena which you know at this deep level of nature. So using this, you can make predictions for observables. So, in a sense, in my course, I will show how this Lagrangian has been constructed. The standard model has been formulated 52 years ago already. The paper by Weinberg was in 1967. And Salam paper 1968, and that was the end of construction essentially of the standard model. So before it was important papers by Glacial, because who actually mostly produced this Lagrangian of the standard model, and in these two final publications it was shown how the particles can get the masses in the standard model. So the Higgs mechanism has been employed, and this Higgs mechanism allows to get masses of gauge bosons and also fermions, quarks and leptons in this model. So what's next? So this is 52 years ago. And actually particle physics essentially started 52 years ago before these dates. Of course, electron has been discovered even before, but can you imagine that 52 years it was this epoch of discoveries of particle physics, developments of main notions. And after that, we have a lot of speculations beyond the standard model. Of course, we cannot just live with standard model, right? So what to do? Is this the end of the story? So people invented a number of extensions of the standard model, physics beyond the standard model. And as I said, nothing yet confirmed, including supersymmetry. So these days, people are taking more and more seriously the idea that maybe there is nothing beyond the standard model up to Planck's scale when quantum gravity is supposed to start to work. Essentially, you need to use quantum gravity, quantum theory for gravitational interactions. So let me make few comments about this beyond the standard model, because this is the main issue of these day studies, and those of you who are going to work on in this field, they will struggle with this finding the physics beyond the standard model. So what are experimental evidences that there is something beyond the standard model? Usually people are saying that there is a dark matter in the universe. Right, it's completely dark matter. which is something which is around us, and it is important to explain structures in the universe, galaxies or cluster of galaxies. It should be something around, which we do not see. They do not emit the light, and it is not clear what is the nature of this dark matter. Some particles, probably. Now, recently, the idea that maybe these are black holes which form dark matter, not just usual which are forming nowadays, but those who were produced in the very early universe, so-called primordial black holes. But these are also objects which you can get in the standard model. So it's not clear that if dark matter are really some physics beyond the standard model. Then we have dark energy. Again, something which is in the universe and which actually rules expansion of the universe, the speed with which universe expands. We don't know what is the nature, again, of this dark energy. There are many ideas. And maybe we do not understand quite well gravity. So that's also one of the possibilities. So still we deal here with gravity, maybe with slightly changed gravity. So that's another open question. And it is not clear if this is really something which belongs to the standard model. Also, within the standard model, it is very difficult to obtain so small dark energy as it is observed. So usually one gets many orders of magnitude bigger dark energy in the standard model. So it should be some cancellation, and we don't understand really the mechanism of this cancellation. Now, another important issue is inflation. And you see many of the things are related to cosmology, to the universe. So, to explain properties of observed universe, people introduced this idea of inflation, so that in early days the universe expanded exponentially fast. For this you need to have some probably field which is not within the standard model, it seems, which provides this very fast expansion of the universe. But even this is not clear because people invented so-called Hicks inflation and discussed this. Higgs field, Hicks inflation. As I said, was attached to the standard model by Weinberg and Salam to give masses of particles. And this is the scalar field, which actually can also serve as inflat on the field, which is responsible for this fast expansion of the universe in the early days. But not just a simple Higgs field, which we see just in the standard model. It should have some kind of particular coupling with gravity. So Higgs field and some non-trivial coupling with gravity. That can produce also inflation. What else? Well, people are also mentioning usually neutrinos and neutrino masses. So that's our experimental. Saying that the smallness of neutrino mass is probably the physics beyond the standard model. And again, it's not clear. Again, the scenario, which is called new MSM, neutrino minimal standard model, doesn't use new scales. We just say that neutrinos are usual particles. They have right-handed components as usual fermions like electron, muon, and others. And all these particles are at electroweak scale and below. Again, it is not clear if you need to go beyond the standard model at some high scales to explain neutrino masses. And by the way, within this scenario, one can explain also baryon asymmetry of the universe, which yet another fact which is considered as something beyond the standard model. So we have protons around us, but there's no antiprotons. And there is a good idea that actually in the very early epoch, universe was symmetric with respect to particles and antiparticles. And this asymmetry is developed in the process of evolution of the universe. So this is a great idea, of course, which belongs to Sakharov. And one possibility is that this asymmetry is developed due to oscillations between, say, usual neutrinos and these right-handed neutrinos. So again, you do not need essentially introduce too much things beyond the standard model. And all these particles are essentially within the standard model. And you do not introduce other scales. So I'm just saying this, that we are kind of at critical condition. So if I would give this lecture, and I gave lectures say 5 or 10 years ago, I was saying, okay, yeah, sure, there are these facts which actually testify, most probably, that there is some physics beyond the standard model. And nowadays people are not sure, because probably this can be also explained within the standard model with some better understanding of gravity maybe. Then of course we have many parameters in the standard model. I don't know how many, I don't know, 20 or so, because all the masses of quarks and leptons in the standard model, they are essentially related to Yukawa couplings which are not known. So we just put this by hand. So bottom line, in the standard model, there are many parameters which are not explained within the standard model. And then people are saying, oh, this is probably testifies that we need to go beyond the standard model. Well, it may happen that this kind of the couplings immediately come from, say, Planck scale, and somewhere at Planck scale, string theory are supposedly give you the values of these Yukawa couplings. So this is also a possibility. Questions?
How about the fact that there are like 3 families for each of the...
Yeah, so this is also open question. Why 3? Some people are saying, oh, this testifies for this so-called flavor symmetry, and maybe some new gauge bosons exist related to these 3 families.
But this, in the case of neutrinos, that's constrained by experimental data of the set boson.
What is constrained?
That you can only have 3 flavor of neutrinos.
Yeah. Well, experimentally, I think within the standard model, there is no explanation why we have 3 families. Why not 2, or why not 4 families? Another important comment, that once you start to produce some theory beyond the standard model, usually you create new problems. Like, for instance, great idea to have grand unification. When you unify quarks and leptons so within one family, and so it's a very nice idea, but then you create a problem with gauge hierarchy problem, which means that you have very high scale and you have electroweak scale, our scale. And in the theory, it's very difficult to keep this stability. So usually when you have some interactions at very high scale, they will tend to give big masses to our light particles which are sitting at electroweak scale. So this is gauge hierarchy problem. So this is one example. So standard model, surprisingly, is kind of theory which doesn't like extensions. So once you start to do something, you usually punish in one place or another. Supersymmetry is great. It seems that you are not punished, but you do not see supersymmetry. And the only kind of, from my point of view, bad thing about supersymmetry is essentially double number of particles. I was starting my education when supersymmetry was just produced. And so you have quarks and leptons, you have gauge bosons, photons, nice. But then to realize supersymmetry, you double number of particles, introducing huge number of new parameters. So this is kind of unpleasant thing. But anyway, I don't want to discuss supersymmetry. I want to jump to string theory also. Now, my course will have 3 parts. By the way, I'm changing every time a number of things in my lectures. And this time I decided to split my course into 3 parts. So the first part, which I would call leptons and hadrons. And what I will do, I will explain or present how particles are detection of elementary particles. And I will discuss discoveries of particles. And so, and then I introduce main notions and concepts. So this is the first part. The second part, I would call it quarks and leptons. And in this part, I will move from hadrons, the particles which we are observing immediately, to quark level. And this is our, now the deepest level of nature we are studying. So from hadrons to quarks. And I will discuss quark and lepton symmetry. Heuristic principle which actually led to a number of important discoveries in particle physics. And the third part will be the symmetries in particle physics. And here I will discuss, first of all, I will explain the role of symmetries in particle physics, arguing that this is main language we are using in particle physics. Well, you need to know this language to really to work in particle physics. And I will discuss phenomenology of different symmetries. Why they were introduced and what is observational basis. And I will discuss physical consequences or consequences of symmetries. Consequences of symmetries. Questions?
And how are the evaluations?
Sorry?
The evaluations is just an exam at the end, or is it different?
Evaluation of what?
The course?
Assessments.
Oh! You want to say the grades? You know, we are using here, so you will have exam. So let me explain how it works. So you will have exercises, and usually it's like 5-6 sets of exercises. So which means you have homework, you need to solve the problems, and you will have a tutorial to check this exercise. In the end, you will have an oral exam. And in oral exam, we have grades here, E, which is excellent,
We know.
then A, B, C, and fail. Okay. Now, in my course, if you are listening the course and to understand what I'm speaking about, it's enough. Even you may not even look at the books. I will give you the list of the books. maybe next time, next lecture. But again, if you understand the course which I'm showing here and presenting, so that is enough to be ready to exam. And the courses, the questions during exam are precisely what I'm discussing during the lectures. So I will not add anything else on the top of what I'm presenting here.
So there's no written exam.
In my course, no. So you will have this tutorial, which actually has some value, so taking into account this. And I may give some very kind of small problem during the exam, and just to solve it, something simple. Okay. So usually, in the first lecture, I'm presenting kind of highlights of the main events during, say, last year. So what happened? So what I can say, LHC, which is a Large Hadron Collider, doesn't work these days. So it's 2 years, and this is the main machine in our high energy physics, which actually was used to discover Higgs boson, and we are still hoping that they will find some new physics beyond the standard model, maybe supersymmetry, maybe not. So LHC is in the phase of upgrade. So the most important, they will have bigger luminosity, so more powerful beams of protons which are colliding. And they may increase a little bit energy, say from 13 TeVs to 14 TeVs. And so these days, people are publishing papers based on analysis of the data LHC has collected in the previous year. So they stopped to work last year in October, at least this proton-proton round. They had also collisions of ions, heavy ions. And so they are publishing many papers producing analysis of the data which they have collected before. So what happens is they collect data, huge amount of data, and then they make analysis of this data and publish. So this is what happens these days. Of course, great discovery, recent, is discovery of gravitational waves. That happened already some years ago, already 4 or 5 years ago. Nobel Prize was awarded in 1917 for this discovery. And people didn't appreciate it maybe in the beginning, the meaning of what has been discovered. And it may happen that studies of these gravitational waves, and now actually many events has been detected. Not many has been published, but now they routinely detect gravitational waves. So it's really kind of quantitative science. And as far as particle physics is concerned, we are still hoping to detect gravitational waves from the early universe, again, primordial gravitational waves, which bring some information, for instance, about some phase transitions in the universe, which in turn related to particle physics content. So, in a sense, by this we are testing some physics, some high energy physics, if you want. Okay, also, what has been detected is just classical gravitational waves. Now, essentially after this detection, the idea that maybe dark matter are just these black holes revived. People start to look carefully. And the point is that what we have observed is merging of black holes with the masses, something like from 20 to 30 to 40 solar masses, kind of particular range. And that may testify that it is kind of close to this range. We have many black holes. And of course, to explain why these black holes are in this mass range. And then the idea that may happen probably because of this, the origin of these black holes is not just collapses of stars, which we usually think about, but something which was produced already in the early universe. Another important event is observation of merging, and again gravitational waves, of merging of neutron stars. again, enormous progress because people understood that maybe the elements like a gold has been formed in these events of coalescence of these neutron stars. I don't want to discuss it. This is really interesting issue, and these days is enormous development in this area. Now I mentioned already neutrino physics, and in this neutrino physics we had still a number of observations which cannot be explained within the standard model, and maybe testify for existence of additional interactions of neutrinos, or maybe even new neutrino species, which we call sterile neutrinos. This I will discuss a little bit in the course. Questions? Okay. So, let me start. That was kind of introduction to the course itself. And the first what I want to discuss is what is the elementary particle. Well, elementary in the sense that this is the deepest level of nature.
Is that?
Sorry?
If you believe in string theory, is that?
Yeah, so that's what we know, right? Yeah. So the deepest level. We don't know what is really realized. So nowadays, these are quarks, leptons, and particles which mediate interactions between quarks and leptons, and these are photon, W bosons, Z boson, and Higgs boson, which give the masses, this field gives the masses of particles, and the outcome of the Higgs mechanism is existence of real scalar particle, neutron real scalar particle. So what is elementary particle? This is quantum object which means that its behavior, propagation, and interactions are described by relativistic quantum mechanics and field theory, quantum field theory. It is structureless. Or, in another words, looks like point-like object. At least at the level of accuracy we have now with our observations. Maybe in 5 or 10 years we will observe the structure of quarks and leptons. But for the time being, they look like point-like objects. So what is alternative? An alternative would be compositeness or composite, so that maybe quarks and leptons are composite objects. And actually people are discussing composite quarks and leptons, and especially W and Z bosons, and also discussing partial compositeness, which means that your particle actually has two components. One is really point-like, and another one has a kind of composition. Now, how we test this? The particle is point-like or composite.
It's good.
Okay, so, right. That's to some extent the same procedure as Rutherford used when he observed nuclei in atoms. So the atoms were looked like at some point as a kind of elementary object, but then Rutherford, using scattering, observed that actually atom has this core using scattering, which has a smaller size, which means that you have in atoms electrons, and you have also this small size core. So scattering, and scattering looks like a microscope. So if you want to look at small structures, you need to use your microscope with small wavelengths, and so irradiate your object by small by light with small wavelengths, and then you are sensitive to the structures which are comparable with the wavelengths of your light, which you are irradiating your object. So which means that not only you need to use scattering of some particles on your object, but you need to use as high as possible energies of these particles, because the energy or momentum is inverse of the wavelength. So wavelengths, since particles have also this wave or quantum mechanical structure, so the wavelength is inverse of the momentum. And so if you want to probe the small structures, you need to use scattering of particles with as high momentum as possible. And that is provided by LHC, and therefore the LHC gives the strongest bound on compositeness. So LHC, Large Hadron Collider, and so with this collider, we scatter protons on protons with total energy in the centrum of mass. Who knows what it is? Who knows what is the total energy in the centrum of mass? No, I mean definition. So it's just, in our case, in the case of LHC, the sum of energies of colliding protons. And so in this case, it's 13 TeVs. This is how it worked. Now, so the plan is 14. So now it was working with 13 TeVs, which means that each of these protons had the energy 6.5 TeVs. And what is TeV? TeV is 1,000 GeVs. And the mass of the proton is around 1 GeV, so that the energy is 1,000 times bigger. TeV is 1,000 times bigger than the mass of the proton. Okay? And here we have something like 6.5 thousandths of proton masses. So this is the energy of the beam. So what we have protons scattered on protons. Let me say in advance, protons are composed of quarks, also gluons, but quarks. So essentially at energies of LHC, protons can be considered as just beam of quarks. All this proton structure doesn't play much role that these quarks are within the proton. So essentially LHC collides the fluxes of quarks and fluxes of gluons. And so this is why we are testing really the structure of quarks and not protons. We established that proton is composite objects long time ago already. Now so we are trying to find out the information about quarks. So what happens? You have proton and you have proton, and one of the quarks from this proton and one of the quarks from this proton, they scatter on each other, and at quark level you have this picture. So you have initial quarks and they scatter at some angle, but then these quarks do not, when they remove from the collision point, they, what we are saying, form the hadron system, hadrons, secondary hadrons. So what you see actually jets as we are saying. So these are jets of hadrons. Which are formed by these initial quarks, which are, so that you have collision of quarks. At first you produce two quarks, and so they form eventually these jets. I will discuss this later. Anyway, so you have events when there are two very energetic jets in opposite directions. And so you can introduce momentum, total momentum of this jet, and transverse momentum, which is kind of projection of this momentum onto the plane or line which is orthogonal to collision. So this is what we call PT, transverse momentum. Remember, in the Rutherford experiment, he observed the structure of the atom because he observed the scattering on big angles. So alpha particles were scattered on big angles, which means with big transverse momentum. The same story is here. So to see the structures, small structures, he observed scattering at big transverse momentum. This is important. Okay? And LHC observed these events and constructed distribution of number of events with a given transverse momentum. And the dependence was like something like that. Of course, bigger number of events when you have smaller PT, and more A events when you have high transverse momentum. This is essentially an analogy of angular distribution in Rutherford experiment, if you will. Now, this dependence is sensitive to the fact if you have your quarks composite or not. So if they would be composite, you would see something like that at some PT maximal. And this PT maximal is 1 over the radius of the structure. Well, in our case, it's quarks. Again, the same as in the Rutherford experiment. If nuclei inside the atom would be just distributed over all the volume of the atom, you would not see scattering with big angle or large transverse momentum. The same is here. So what has been observed, that there is no such a change or cutoff, and the observed dependence is well in agreement with what is expected for point-like objects.
Why is that? Why you have a cutoff when you have a structure?
Let me do the following. I will have a lecture about this when we will discuss transition from the protons to, or I will also mention this Rutherford experiment. Okay, so because you need to have hard collisions, so you need to have small, what is this, impact factor, if you remember what is this. Okay, so if you have something like if your charge is distributed in big volume, then you would have even according to quantum mechanics if you want, but also there's a classical analysis. Then the biggest momentum transfer will be inverse of this size. Or imagine that you have scattering with this impact parameter. Then what happens is, so you have incoming particle, then the charge which actually produces your scattering is inside the sphere which is given by impact parameter. And this charge doesn't contribute because of the spherical symmetry. And so you'll have scattering like this, which is smaller than if all the charge is concentrated in small, very small volume. Then you would have scattering with this small sphere, and it will produce bigger effects. But I will discuss this and write the formulas later. Okay? So if your charge is distributed, then you have soft interactions. You need really to have your charge concentrated in very small volume, and then you will have, even for small impact parameter, then you will have big angle. So, what has been found? That since we do not see any deviation from this point-like picture, we have found that the radius of quark should be smaller than this P transverse maximal, up to which you do not see any deviation. So essentially, so everything cut somewhere here because that is related to maximal energy in your experiment. So the maximal transverse momentum would be 6.5 TeVs. And that gives you this bound on the radius of the quark, which should be 10 to the minus 18 centimeters. This is essentially inverse of these 6 TeVs, if you express this in terms of distances. Well, let me, for comparison, remind you that the radius of proton is about 10 to the minus 13 centimeters, which is 5 orders of magnitude bigger. And the radius of weak interactions is something like 10 to the minus 16 centimeters. Okay, so this is proton, proton. And this is weak interactions. Okay? So it's quantum object, or it's elementary particle. Quantum object, structureless, at least as we measure it now. Then this object is described by a set of characteristics. Or maybe you have some questions to that. Again, I will discuss in details what is this connection of maximal scattering angle or transverse momentum and the size of, even twice, because we first will discuss the slip of the reservoir experiment, and then it will be a discussion also of the structure of protons themselves when we came from hadron level to quark level. Again, the same story, scattering, and then we observe that scattering looks like it proceeds at very small objects. This is how we actually discovered partons and quarks. Okay? So the third is that this object is described by a set of characteristics of particle. Parameters like mass and quantum numbers. There are two categories of quantum numbers. The first one is so-called external characteristics. Quantum numbers. And those are masses. This is Lorentz invariant, and m square is energy square minus p square. It's Lorentz invariant. Then spin. And parity. All these characteristics are actually characteristics of motion of particle in our space-time. They are connected to certain symmetries and transformations of our space-time. Like, for instance, this one is shift in space-time. This one is rotation. And this one is reflection. When you change x to minus x. So this actually is not contained in rotation. So that's spin is characteristic which kind of describe particle with respect to rotation of the space-time. I assume that you learned already this, right? But what is again important that this is, all these characteristics are connected to certain transformations of space-time and certain symmetries. And this actually already gives you some idea why the language of particle physics is the symmetries and notions of the symmetries. So these are characteristics of propagation. In space-time. Essentially free propagation. Okay? Now, what are internal characteristics? Electric charge, for instance. Then color. I will discuss what is this later. Then isospin, weak isospins. Total weak isospin and the surge projection. Hypercharge. Let me continue here. Baryon number. Lepton number. All these characteristics or quantum numbers are characteristics of interaction. So, while here these are characteristics of propagation, those are characteristics of interactions. So these parameters have been introduced studying interactions of particles. And I will explain why we introduce these quantum numbers in such a way and what are kind of experimental basis for introduction of these characteristics. So what these characteristics are giving for us? Classification of particles. By the way, probably I should add that this characterizes electromagnetic interactions, obviously, right? So these are strong interactions. These are characteristics of weak interactions. So they provide classification of particles, selection rules, and conservation laws. Like, for instance, conservation of electric charge in our processes. And some of these characteristics are giving the coupling constant, or the strength of interactions, coupling constant. Sorry, it's the angle. Coupling constants. Now the question is, so those characteristics are related to some symmetries and transformations. And how about these characteristics? They also are related to symmetries and transformations, but not in usual space-time, but in some internal space. So we are introducing internal space and symmetry in internal space. And those are kind of characteristics of transformations or symmetries in this internal space. And I will discuss this at length, especially in the third part of the course. So, bottom line is that the particle is some structureless object characterized by a number of these parameters and characteristics. So that's particle, and it is characterized by mass, spin, usual charge, color, I3, Y, B, L. And all these characteristics are associated with certain symmetries. And this is why symmetry is universal language in particle physics. So those are characteristics of unparity. This is external, and these are internal. Once we know this characteristic, this means that we know the particle. So, and we think that this is complete description of a given particle, once we know all these parameters. What does it mean? Of course, you know, electron is not some ball which is written that it is electron, right? And this is, it has charge -1, and lepton number is 1. So we introduce these characteristics. It's not like it's something which is, so we introduce to describe certain properties and features of interactions. Once we know all these characteristics, we can predict how the particle will behave, right? We can completely describe how the particle is moving, how it interacts with targets, different targets, and what are observables. We can predict what will be observable in these interactions. In this sense, this gives for us complete description of elementary particle. Let me make a comment on what is called reality and models. Which actually reflects of what I was just saying. So we have something, some object which we do not see by eye, we do not see, we see some kind of secondary effects of these elementary particles. Nevertheless, we can describe these particles as we think. And of course the question, which we are always asking, is this description complete or not? Or maybe there are some additional parameters, or some hidden parameters. For time being, we don't know this. So maybe at some point we need to introduce some more parameters. Maybe we'll discover some new interactions of this particle. Very weak, maybe. But for time being, it looks like that provides a complete description. The second one, the second question, is this description exact or approximate? Again, it may happen that, maybe there are some new interactions and which give very small corrections to what we know now. So it's not excluded that this is also approximate description of elementary particle. So this is our model of elementary particle. Set of parameters which we produce. So the electron doesn't know that he is electron and he has electron number 1, right? Or some -1. This is our notion. This is how we think about this object. And of course, the question is again, maybe I need to use another set of parameters to describe this object. Why we introduce those parameters and not other parameters? Okay, think about this.
These parameters are necessarily conserved?
Not all. Well, electric charge is conserved. This is conserved, but those are not conserved. Electron number is not conserved. For instance, we have oscillations, which is testifying that they are not conserved. So they are good quantum numbers. And of course, if something is conserved, then this is very good, right? If it is approximately conserved, then the question is if there is any sense to introduce this parameter, and what is the sense to introduce this approximately conserved parameter. Of course, if something is broken very heavily, then not much sense to introduce it. So what we are doing, in fact, we have our formalism, we have our model, we have these kind of parameters, we have some symmetries, we have group theory, which you learned, right? So this is our formalism. And essentially what we are doing mapping of what exists in the real world onto our mathematical formalism. This is more like a philosophical even discussion, because we have our mathematical formalism, and group theory has been invented much before this particle physics has been developed, right? And suddenly we see that this theory has some correspondence in the real world. Okay? This is very non-trivial. So why we have this mathematical formalism which has some kind of relation or connection to some reality which exists. So it looks that, yes, so we have this mapping of our observations. So we have some observations. We introduce some notions. And so knowing this, we can make some predictions. And now we are testing these predictions, and if everything is okay, if we have agreement, then we are kind of confident that our description is correct. Okay, so this is the only what we can do. Now, what is connection between this mathematics and some kind of physical objects? Well, it looks that there's kind of unity in the world. I don't know how to even more precisely to express. So it's maybe not accidental that we have our theory and it gives correct mapping onto what happens in to real world. So let me. I think I had something to write. So we have model, and we have real object or particle. And here we are doing mapping. Of our kind of notions in our model, mathematical formalism, onto real observations on reality. Questions?
Does this model describes all the real objects or only certain properties?
Well, standard model, it seems, describes everything. That's what we.
Not gravity. Not gravity.
Plus gravity, yes. Gravity for time being is in particle physics. I don't know what is quantum gravity still. But in particle physics, standard model, it seems, describes everything.
There is no oscillation in neutrino oscillation.
Well, this is a question: should we include oscillations or masses in the standard model? This is kind of matter of definition, how you define the standard model. But it looks like, the standard model was developed before we discovered these oscillations, of course, right? And majority saw that neutrinos are massless. And they are massless because there's no right-handed components in the standard right-handed components of neutrinos. So the left-handed, I will discuss this at length later. And so they are saying, let us not introduce right-handed components because automatically we get massless neutrinos, which is kind of distorted logic from my point of view. So why all the particles have left and right components, fermions, but neutrinos have not? Once you introduce right-handed components, then you get masses. So the question is, should we include right-handed components of neutrino in the standard model or not? Essentially, that your question is reduced. I would include this. This is kind of, from my point of view, kind of historical stupidity, if you want, because that people made this easy life. They say, okay, nothing to explain. There's no right-handed components of neutrinos, and within the standard model, unless you introduce some non-renormalizable interactions, neutrinos are massless. Dot. Neutrinos are massless. There is no. Now people are saying, oh, we observed oscillations, and therefore neutrinos have masses, and therefore this is the physics beyond the standard model. What is? It may happen that all this you have right-handed components. These right-handed components even have the masses as, say, top quark or big quark or something. What's wrong with this? Okay. Now this is the part which I'm usually presenting in my lectures. And this is part devoted to units we are using and scales. In high energy physics, we are using the system of units where velocity of light, Planck coupling constant, and Boltzmann constant are just one. So this is velocity of light. have relation between energy and mass. So since C is 1, means that the measured energy in the same units as the mass. Now we have P equal mc, which means that also momenta have the same dimensions. And energy, if you have, say, gas, average energy of particles in the gas is 3 kT. This means that we measure temperature also in the same units, and we will measure everything in energy units. So this is how it is accepted in particle physics. So energy is the main unit. And therefore we use, for instance, for mass measurements, not grams, but again energy units. We are saying that the proton has the mass 1 g or 938 MeVs. So energy is main unit, and we are using electron volts as measure. So 1 electron volt is the energy which particle with electric charge 1 acquires when it crosses the difference of the potential, which is 1 volt. So if you have V potential, which changes with distance, and it changes by 1 volt, say from 0 to 1 volt, then particle with charge 1, which actually crosses this, will acquire the energy 1 electron volt. So 1 electron volt is 1.6 10 to the minus 12 ergs. Well, you will have some exercises just to have more experience with this. And 1 electron volt is 1.16 10 to the 4 Kelvin. And for instance, temperature of CMB radiation. This is radiation which fills all the universe and which actually is a residual from Big Bang and the early epochs of the universe. The temperature of CMB is 2.7 Kelvin, which in our units is 2.3 10 to the minus 4 electron volts. Okay.
And we can say that the energy of the units of inverse length as well.
Sorry?
And we can also say that the energy of the units of inverse length.
Yeah, so I will discuss this actually. But let me first to give you the ideas about these energy scales. Yes, we can measure distance in inverse energies. And also time, we can measure time in inverse energy. So that's really universal. I'm showing this figure with making some editing, but more or less it's the same all the time. So let me put the energy scale in nature and in particle physics. Well, this is energy scale. Sorry, it's not very straight, but to some approximation. So let me put here 1 TeV. And then, let's see. So it's 1 TeV. Then I will go back. It will be 1 GeV. So what is this? 1 GeV at 1 giga electron volt. So it's 10 to the 9 electron volts. So this is energy scale. this is tera electron volt. So this is GeV or giga electron volt. This is tera electron volt, which is 10 to the 12 in electron volts. So let's go further. This is PeV, 1 PeV, and this distance is 3 orders of magnitude. Then there's 1 EV. So let me see. Then I don't know how to call it even, but some name probably exists for this. So that's PeV is 10 to the 15 electron volt. This is 10 to the 18 electron volt. Let me switch here to GeV. So this is 10 to the 9 GeVs. So that's, let's go further. That will be 10 to the 12 GeVs. That will be 10 to the 15 GeVs. 10 to the 18 GeVs. I think that will be enough for me. That will be 10 to 15 GeVs. So let's go to low energies, GeV, and next is 1 MeV, mega electron volt. Then it will be 1 keV, kilo electron volt. Then 1 electron volt. Then it will be 1 milli electron volt, which is 10 to the minus 3. Now let me stop at 10 to the minus 6. And now let me put particles which we know on this scale and the important energies. So the electron is sitting here. This is the mass of the electron. And I think you need to remember at least some of these masses. So all the point is that if you want really to work in particle physics, you still need to remember something. You cannot probably be right. But some important skills you need to know. And you need to know how to reconstruct all other skills out of knowledge of few scales. So M, mass of the electron, is 0.511 MeV. Okay? Now, the proton is sitting here, so this is mass of the proton. It's another benchmark. And mass of the proton is 0.938 GeVs, so close to 1 GeV, but at least these are famous 2000 mass difference, mass ratio. Now the heaviest quark which we have observed, what is it? Who remembers? Top quark. Top quark is 175, 173, which means I put here top quark is, this is 10, this is 100, somewhere here. So this is mass of the top, sitting somewhere here. Now LHC has the total energy in the center of mass, as we discussed, 13 TeVs, which means that the maximal energy is somewhere here. Here is energy of LHC. So you see, this energy is bigger than all these masses, which means that you can copiously produce these particles at LHC. And to produce something, you need to have energy which is at least bigger than the mass of the given particle. Now what else? Let's go further. The important particle is muon. Muon is lepton, like electron, but heavy, 200 heavy. So it's a 105 MeV. So the muon is somewhere here. And another important particle is pi. which is supposed kind of producing strong interactions. At least in the old days, people had this, Yukawa had a theory in which pi mediates the strong interactions, and the mass of the pi is 140, so very close to muon. So that's here is m pi. What else? So if you go low to lower energies, then atomic phenomena are at energies keV. Here is atomic phenomena. Energies of atomic levels, and if you have emission of photons or gammas, so they are in this range, in keV range. Then what we have neutrino masses, and neutrino masses are below 1 electron, below 0.1 electron volt. So it seems that at least one of neutrino mass should be somewhere here. Maybe the lightest neutrino, and they have 3 neutrinos. The lightest may be massless, so it can be 0. Right? But at least the second one should be 10 to the minus, so it should be somewhere here. The second one, so it's this heaviest, and one should be here, and 2. Here. Now interesting scale is the scale of a cosmological constant, which is 10 to the minus 4 electron volts. This lambda cosmological constant. And people speculate that since neutrino masses are kind of close to this cosmological constant, maybe somehow this cosmological constant is related. It's not constant, and maybe it's related to neutrino masses, and there are some...
In what volume? In what volume? Because we know the energy density of their energy, but no...
Yeah, it's a 4 square root of this energy density. That's 10 to the minus 4 electrons.
So in some volume, right?
Right, so energy density, right.
Okay.
Yeah. Now important scale is electroweak scale. Oh, maybe I should first say the scale of strong interactions. This is something like 200, 300 MeVs, not far from this mass of the pi. So that here is a lambda QCD. Lambda QCD, this is the scale of a strong interaction, is 200, 300 MeVs. Now the scale of weak interactions is 260 GeVs, and so that's this is GeV. This mass of slightly bigger than the mass of the top quark. So this is lambda electroweak. So this is electroweak scale, which is given by so-called Fermi coupling constant. We will discuss what is this. But this is something like 260 GeVs. So interestingly enough, the mass of the top quark essentially corresponds to Yukawa coupling 1, because mass of the top quark as well as other quarks is Yukawa coupling multiplied by this electroweak scale. With square root of 2, you get precisely the mass of top quark, which is kind of an interesting hint to what's going on. So that's it. So this is what we know. Now, of course, we know that there are Planck scale, which you can make out of gravitational constant, Newton constant. So it's somewhere here, lambda Planck, which is 10 to the 19, 1.2 10 to the 19 GeVs. Here, slightly smaller, people are saying there's a string scale, in fact, 10 to the 18 GeVs. There is another scale, which we don't know if it exists or not, so-called scale of grand unification. And in supersymmetric models, this scale is somewhere few 10 to the 16 GeVs. So somewhere here, maybe you will have lambda grand unification. So what is the scale? At low energies, we have three different interactions: weak, electromagnetic, and strong interaction. And we have three different couplings. Of course, weak interactions have, so electromagnetic have the smallest coupling, then there's weak interaction, and then there's a strong interaction. The couplings are not really couplings. If you take into account quantum effects, then couplings actually change with momentum. And it happens that all the three couplings may be of the same size at this grand unification scale, which may give some hint that maybe there's something interesting happens here. And all these grand unified theories are built on this idea. So unfortunately, we have no confirmation of this. We haven't found yet proton decay, for instance, which is one of the predictions of this grand unification. So I will stop at this point. I will continue a little bit next lecture. So questions? And of course, see, you don't know what is here. People usually call this as deserts. There is nothing here, there is nothing there, and there's an island, this one, and there is something here related to neutrinos, another island. You may see this picture in a different way, maybe in more kind of productive, because eventually we should find out what is behind this picture, so what is behind the spectrum. Well, probably I can say also that we also have data on cosmic rays. We study also high energy cosmic rays, and one of the important discoveries recently was discovery of cosmic neutrinos of high energy. So this is neutrinos of cosmic in PeV range. So that's interesting. Some events are here. And why I'm putting this scale? Because there are some ideas that maybe these neutrinos are originating from decay of very heavy particles. So maybe there's some another mass scale exists here in PeV. And the highest energy cosmic rays are 10 to the 21 electron volt. Let me see. This is 10 to the 50. So this is high energy. Highest energy is cosmic rays. This is what we have observed. So this is the picture. Questions?
What are the energies of some of the hypothetical particles, like graviton, for example?
Like graviton, well, zero. We think that it is zero unless you introduce some modified gravity. So, of course, we have also photon. And I will actually, so let's go to zero.
Where is the Higgs?
Oh, Higgs is 125, right? So, sure, let's write Higgs. Higgs should be somewhere here. So this is mass of the top, and it should be somewhere here. And mass of the Higgs. Top is maybe I put here too close to 100. So top is here, and the Higgs is somewhere here in this scale. 125 GeV.
Is there any way to know the energy scale from a given model? I mean Lagrangian. For example, electromagnetic.
Well, you know, there is no scale essentially. We have scale, the so-called Landau pole, where this coupling becomes infinite. Otherwise, it's massless. Photon is massless. Now, this is one of the major problems. We don't know the origins of these scales. We don't know the origin of. So, what are the key scales? So the key scale is this electroweak scale, which is 126 GeVs, and we don't know what is the origin of this. So other particles, they are connected to this scale, like masses of electron, masses of muon, pi. I have not put here mass of W boson, which is very important. So here I can put mass of the W boson, which is intermediate boson responsible for weak interactions. So it's somewhere here. Now all these particles essentially hang up on this scale, all these guys. Well, with neutrinos maybe some special story. Maybe one needs to introduce some other source of masses apart from usual standard Higgs boson.
So how the scales are determined by experiment?
That's experimental fact. These are experimental facts.
Two questions. As you said that the masses of neutrinos are not exactly beyond the standard model, but maybe the mass generation mechanism should be beyond the standard model physics.
So it's open question. It may have, neutrinos may have again very small Dirac masses like all other, like electron, like muon, like quarks, but you need to have a very small Yukawa coupling. That's a possibility. But of course there's a lot of mechanisms beyond the standard model to explain the smallness of neutrino mass. So it may happen that the smallness of neutrino mass is due to existence of another scale which may be somewhere here. So that's like 14 or 12 GeV somewhere here. So-called seesaw mechanism, which is based on existence of Majorana masses of right-handed neutrinos. So on the top of usual Dirac masses, you introduce also Majorana masses, which break lepton number.
Also, from the picture, it apparently seems that it works more to put efforts in experiments like IceCube rather than LHC.
Well, if you want to discover new particles, so IceCube, this is, let me just, because you asked, IceCube is this under ice detector in Antarctica, and actually these cosmic neutrinos were detected by IceCube, so in this PeV range. Now, if you want to produce new particle, what matters is not just energy in some scale, but what matters is in energy in the centrum of mass of colliding particles. And then you will see that actually there is no big advantage, at least for those neutrinos in comparison to LHC. So that's important difference, because just energy of a forgiven particle doesn't tell you anything. You can go just another reference frame, let's say you will have higher energy or even higher and higher. So what matters really is the total energy in the centrum of mass of colliding particles. This is available energy, and actually it's just material which will be later. So that, of course, if you use these cosmic rays of very high energy, here you have advantage with respect to LHC. The problem is that these high energy particles are too rare, so the fluxes are too small. And you may produce some new particles using these very high energy cosmic rays, and people of course explore this. But there are two things. One is that the flux of these particles is extremely low. The second one, you need to find a way to identify some observables which correspond to production of new particle. Because usually at these very high energies you produce so-called atmospheric showers, which means huge number of usual standard particles, pions or protons, and then you need to find a way to kind of to dig up something which is extremely difficult. So for instance, we cannot find supersymmetry because it's just even if it is a TeV scale, it's difficult to identify.
Uncontrolled experiments. Are uncontrolled experiments.
Well, to some extent, yeah. Of course, we can learn various things from this.
You said that the highest energy cosmic particles are about 10 to the power 21 energy.
Electron volts.
Yeah,
No, electron.
sorry, electron volts. So actually, I want to confirm something. Some time ago, I learned that the particle that was found with that energy was named Oh My God particle. Is that correct?
Which particle?
It was found in Utah, I think in 1991. It was named Oh My God particle. Is that correct?
Well, this I don't know. It's
It was written on Wikipedia, so I don't know if it's correct.
well, again, so here, actually, this 10 to the 21, it is already so-called GZK cutoff range where the flux drops down substantially. But tell me, just how you call this, maybe?
Oh my God.
Well, I don't know. This is not widely accepted term. So they saw such events. That's true.
So was it discovered in Utah by Fly something called telescope, Fly Eye telescope?
Oh yeah. So okay. So we will have lecture on cosmic rays, and I will discuss this. But what do you want to say? So this is the highest energy particles which have been found, 10 to the 21. Yeah, somewhere here. Where is 21? So it's somewhere here. This is 10 to the 21.
Rest mass, didn't it?
This is the energy, electron volts, of these huge, extensive air showers. But there are just few events of this type in this range. You cannot. Okay? Let's see you tomorrow. This one.